Okay, once you check your cake appearance, hopefully one of the three formulation will give you a good, nice cake appearance. Okay, and then the second thing you want to check is the reconstitution time. So normally the freeze-dried products should be reconstituted before they're used, right? So since water molecules are removed, you have to add back the water molecule before you use. So I'll show you how to use the sterilized needle, syringe needle, to get the woofy and then inject that woofy back to your freeze-dried drug vial. So after adding that, in this case 2 mL, because that's what you started your freeze drying process, right? So 2 milliliter of woofy will be added back to your freeze dried product, and then normally the requirement is your reconstitution should take less than 2 minutes with not much of the effort. Okay, so after adding 2 ml of sterilized woofy, you should be able to easily reconstitute your freeze-dried drug pack back to the solution. Okay, so that should be done without much of the vigorous shaking. Okay, so gentle maybe shaking should be able to demonstrate that, and see if all your three formulation will be able to give you that gentle reconstitution within 2 minutes. If any of the formulation is not giving you full reconstitution within 2 minutes of time, and that's probably not good. Okay, write down your result. And the next thing you need to check is the osmolarity of your formulation. Okay, once you have reconstituted your freeze-dried drug, you need to check the osmolarity, which is the salt concentration in your formulation. Okay, so for this method, we need a machine called osmolarity measurement. Okay, so we will use the BAFRO of 5600 osmometer. Okay, that's what we have in the lab. Okay, so using that machine, you will check the osmolarity of your freeze-dried drug, 3 different formulation. Okay, so with any other instrument, you have to calibrate this instrument first. So we have the standards. You will be using 3 different standards at 3 different osmolarity to calibrate the machine. So this is the step. Procedure you need to follow. Turn on the osmometer first and then do the calibration. So 290 millimole standard, and then see if your osmometer reads it the right number. If not, you have to adjust that, and then do another one at 1000 millimole per kilogram standard, and finally 100 millimole kilogram standard, and make the calibration. Once that's done, you can add your sample that's reconstituted and see what the osmometer you're going to get. Okay, so what's the requirement? So normally the isotonic condition is the best, right? Isotonic, whatever the salt you have in your bodily fluid, should be the best, because it doesn't cause any pain when your injectable drug is injected, if it's isotonic. Okay, so then isotonic means what? Then if you have human plasma, okay, your blood, okay, without your blood cells, that osmolarity is about 290 millimole. That's why we're using 290 standard. Okay, so that's about 285 to 310 osmomole per liter. So that's okay within that range. If you see it, if your formulation will give you around that area. If not, that could be a problem. Okay, and then the last thing you need to check is the residual water content in your freeze-dried product. Okay, so residual water content. So if it's well freeze-dried, okay, throughout your freeze-drying process, the residual water content in your freeze-dried cake should be less than 1% of the total weight. Okay, freeze-dried product. Okay, less than 1% is the desirable water content. So you need to measure the water content in your freeze-dried product with some instrument that can detect it. In our case, we'll use the instrument called Carl Fisher titrator. Okay, so this is the Carl Fisher titrator. They may come in this shape, or they may come in the one we have in the lab. So that's the mostly widely used residual water content measuring instrument. Okay, you can measure between parts per million or milligram per liter all the way up to 100% water. Okay, so it's good. So the one we have is a Fisher colorimetric machine that we have in the lab. Okay, so this instrument is good. So you're going to learn about different instruments that can measure water content, maybe 3 different kinds in the lecture, but this Carl Fisher, it has these advantages. It's fast to do the assay. It's very selective for water and very accurate and precise, and you can measure a wide range of water content in your sample, and during the measurement there's no decomposition happening. So basically it's very accurate measuring instrument. But the disadvantage may be you have to handle some chemicals, and some of them may be toxic, and you have to standardize your instrument whenever you use it. Okay, so that may be a little tough. Okay, and how does this machine titrator works? Okay, in that I guess mixing stirring chamber of the Carl Fisher is right there. Okay, you have these 2 different reactions going with the chemicals. Okay, so maybe methanol or ethanol. Instead of using water, of course, you cannot reconstitute your drug with water, then it's going to be full of water, right? Your drug should be reconstituted with different solvent. So maybe alcohol-based solvent, maybe methanol or ethanol. Okay, you will use one of those, or different solvent, either totally different one. You will use something else, maybe. So in your assay, you will use formamide solution, strong organic solvent, instead of water or alcohol. Okay, so anyway, in the Carl Fisher reaction chamber, these 2 reactions are happening. Sulfur dioxide, and then the maybe ethanol is being mixed, and there's a base solution in the chamber as well. So this conversion is being happening in your reaction chamber. So you're going to have some alkyl sulfide that's being made. Okay, and to the alkyl sulfide, if you add your sample, whatever the amount of water is there will be used up during this chemical process. The alkyl sulfide will react with iodine that's existing on the electrode, and then water that comes from your sample, and then it will be converted to this chemical compound. Okay, during this conversion, there's an equal ratio of iodine and water that's being used up in this chemical process. So when this iodine is reduced during this conversion, iodine will become iodide. Okay, and then that amount of iodide that's being made can be measured through this instrument. So the sensor can detect how much of iodide is being made through this chemical conversion, because the amount of iodide it is converted from iodine is actually the equal ratio with the amount of water that you used, because the water is required for this conversion. Okay, so the same amount of water and same amount of iodine is used for this conversion, and you're going to get iodide, that's a reduced form of iodine that's being made, and that iodide can be detected by this instrument. So so 0 iodide is about 0.54 volts, so that conversion is being done on this instrument. Okay, so that's what you are measuring actually. So this conversion is being made, so iodine becoming iodide, and then that that hydrogen ion conversion that's being made. Okay, so this Carl Fisher is a very good instrument. It may come in volumetric Carl Fisher titrator or colorimetric titrator. The one we have in the lab is the colorimetric titrator, which measures a smaller amount of water in the reaction, but volumetric can measure larger volume of water. So for our purpose, freeze-dried, the vial has very little bit of water, so we're going to use colorimetric Carl Fisher. Okay, so once you detect the amount of water, residual water in your Carl Fisher titrator, you have to convert that amount, residual water, into the percent moisture within your formulated drug by using this equation, because you have to consider the solvent moisture, solvent weights, total sample weight with the dried pack and everything. So it's kind of complicated, but that's all right. I have that equation written in your Excel spreadsheet, so you can just plug in the numbers. The Excel will do the calculation for you. So anyway, take a look what it looks like. So here's the protocol you need to follow when you use the Carl Fisher titrator. So you have to turn it on, and then there are some buttons you need to press and start, and there's going to be stir bar spinning, and then the residual amount of water that should be removed, and then once it's ready, and then you have to inject the drug that is solubilized with the formamide into the chamber. So you need to follow that, and if you follow all this process, okay, then you can get the residual water content. It's complicated then. Anyway, that whatever the water content you got should be entered into the equation on the Excel spreadsheet. Then it'll do the automatic calculation for you. So based on that, figure out the percent water content. Okay, when you get to do the lab face-to-face, I'll go over this more detail. Okay, with the Excel spreadsheet and everything. So anyway, so see if your water content is less than 1% or not. So you're basically measuring 4 different parameters out of freeze-dried drug product. Cake appearance, reconstitution time, is it less than 2 minutes? Osmolarity, is it isotonic or not, just like your plasma? And the water content, residual water content on your freeze dryer. Okay, if I show you maybe the Carl Fisher moisture content, the equation, so you'll be measuring out these weights and things. You enter those, and if you enter all those, it'll do the automatic calculation for you, because it's all developed in this formula. Okay, so you will get the percent water content. So I'll go over this with you together. Okay, so that's it.